By now we know how to integrate both sin x and cos x, and we have explored the substitution method. So when we are confronted with the integral of sine squared x and the integral of cos squared x, do we have the tools to evaluate these integrals? Let's start with the integral of sine squared x. Can we do it? If we were to attempt a substitution, what might we choose? It would be reasonable to think, okay, let's try the substitution u equals sine x. That way I will get the integral of u squared. But what about the relationship between du and dx? We know that in this case du dx is cos x, and so du is equal to cos x dx. But nowhere in our original integral do we have a cos x. So this makes it a little bit tricky. And we encounter the same problem if we try and find the integral of cos squared using substitution methods that we've already learnt. So we need to do something a little bit different. So let's go back to the sums and differences of angles formulas, and we'll start with something that is available on your reference sheet. And that is cos of a plus b is equal to cos a cos b minus sin a sin b. Now anything that I write in red is available on your reference sheet. So this one is there. Now what would we do if we want to come up with the double angle formula for cos? If we set both a and b equal to x, we get the following. Now x plus x, that's just 2x. And so we get cos 2x is equal to cos x multiplied by itself is cos x squared, and the same with sin x multiplied by itself. And so we get this double angle formula for cos. And what's great about this is it involves both cos squared and sin squared. And remember, that's what we're after in this video. We are trying to find the integral of both of these. But we just want to focus on one at a time. So is there anything we can do to this equation so that it only has cos squared x in it instead of sin squared x? At this point, we should think of the Pythagorean trig identity, which is cos squared x plus sin squared x equals 1. And this is also on your reference sheet. Now since this is true, if we just do some rearranging to make sin squared x the subject, we see that sin squared can be replaced with 1 minus cos squared. And so therefore, looking back at this last line of working, we can say that cos 2x is equal to cos squared x minus, and now we will replace sin squared with 1 minus cos squared. When we tidy this right hand side up, we notice that the two negatives here make a positive, and so we have cos squared plus cos squared, or 2 lots of cos squared x minus 1. Now adding 1 to both sides, and I will just flip things as well. So let's put the 2 cos squared x on the left, and then we've added 1, and we have our cos 2x here. So the last step to get cos squared x by itself is to halve both sides. And so we now have an expression for cos squared x that doesn't involve any squares at all. This expression here is something that we will be able to integrate. Now, this expression is not on your reference sheet, but what is the more generalized version. We are dealing here with the specific case where n is equal to 1, but this generalized case allows you to project. So you could say cos squared of 2x is equal to half outside of 1 plus cos 4x. Or you could say cos squared of 3x is equal to half outside of 1 plus cos 6x, and so on. So we have our expression for cos squared x, which is great, but what about sine squared x? Well, what we can do is use this original double angle formula for cos 2x, and instead of substituting out the sine squared x, let's substitute out the cos squared x. So what are we going to replace cos squared x with? Well, that's just 1 minus sine squared x. And so now when we collect like terms, we have 1 minus 2 lots of sine squared x. Doing the same thing as before, rearranging, we can add the 2 sine squared x to the left-hand side, and then we can subtract the cos 2x. Finally, we just need to halve both sides. And so we end up with an expression that's very similar to what we had before. And once again, the generalized version, which has an n in it, this is on your reference sheet. So let's use these two formulas that we've come up with to integrate cos squared and sine squared. When we replace cos squared x, let's put the half out the front of the integral, and then we can write the rest, cos 2x, or 1 plus cos 2x, after the integral sign. Integrating 1, we get x, and integrating cos 2x, well, the integral of cos is sine, but we need to account for what's happening with this 2x, so we get a 1 over 2 out the front of sine 2x. Plus our constant at the end. Distributing the half, and we get half x plus a quarter sine 2x plus c. And so this is the integral of cos squared x. Now, because sine squared x can be replaced with an almost identical expression, where the only difference is this minus instead of a plus, that means our final integral comes out to look almost the same. We just have a minus here instead of a plus. Now, neither of these identities are provided on your reference sheet, but with what is provided, it is quite easy to generate these yourselves. Okay, let's have a look at two examples to finish off this video. Number 1. Find the exact area under the curve y equals sine squared x plus 1 between x equals 0 and x equals pi on 2. Now, because this question is asking for area rather than just the value of the integral, we need to be aware of where this function might lie in relation to the x-axis. Remember, any area that is above the x-axis, we will get a positive definite integral, but any area below, we will get a negative definite integral. And so that's important when we're considering area. However, let's look at our function. Because sine x is sine squared x, this is always going to be positive, isn't it? Anything that's squared is always greater than or equal to 0. And then adding 1, well, that just definitely makes sure that it's positive. So for this question, we can just go ahead and find our area by evaluating the integral. So it's between 0 and pi on 2, and this is our function. Now, based on the work we've already done, we know what the integral of sine squared x is. Remember, if you forget, just perform the substitution, where sine squared x is equal to this. But fast tracking a little bit, we saw that the integral of sine squared is half x minus 1/4 sine 2x, and then we also need to deal with integrating this 1, so that is simply x. This gives us two terms that involve x, and so we can collect like terms to simplify this a little bit. Half x plus x, well, that's 1.5, or 3 on 2 lots of x, and then this part remains the same. All that's left for us to do is apply the fundamental theorem of calculus. So let's first substitute in pi on 2. Now here, when we substitute in pi on 2, this gives us 2 lots of pi on 2, which is just pi. And what about when we substitute in 0? Well, 1.5 times 0 is 0, and then we have minus 1/4 sine, and 2 lots of 0 is 0. Our first fraction, 3 on 2 times pi on 2, that becomes 3 pi on 4. And then we ask ourselves, what is sine of pi? And thinking of our sine graph, that's just 0. Now we have a minus sign, and then, well, we've got our 0, but what's sine of 0? Well, that's also 0, so this whole thing is just 0, and we actually end up with an exact area of just 3 pi on 4 square units. Alright, example 2. Find the integral of cos squared 9x. So this is where our reference sheet comes in handy, as we can use the cos squared nx formula. In this case, we can see that n is equal to 9. And so we can replace our original integral with the following. Once again, we'll put the half out the front, and we have 1 plus cos of, well, we want 2 lots of n, or 2 lots of 9. So that's cos 18x. When we integrate, the 1 just becomes an x, and the cos, well, cos integrates to sine. The 18x means that we need a 1/18 out the front. And then we are left with sine 18x afterwards. because this is indefinite, don't forget the plus c. And if we wanted to expand this 1/2, we get half x plus 1 on 36 times sine of 18x. But leaving it in this factorized form is obviously fine as well. Okay, that concludes our video. Good work.